Human beings communicate with each other using language. Computers use languages too, but they don't really look, at least not yet, like human languages. In this next module of videos, we're going to look at the question of how we take our human language and turn it into something that we can use to communicate with machines. This isn't going to be a full course on language design like you might study later. Rather, just as in the first module, we're going to take a look at the foundations, to the basics of our language, to see what works in every computer language you might choose to study or use. So, what aspects of language are usable by computers? Well, keep in mind that computers, as much as we might suspect otherwise, do not actually think and cannot process language, really cannot process anything other than bits. But this connection to bits gives us a way to bridge human language with computer operations. We can use the bits to represent the two opposing states of true and false. If computers process bits, they can process truth values, sometimes called Boolean values in computer languages. A 1 usually represents true and a 0 represents false. So if we restrict human language only to those statements that can be validated as true or false, that's how we can talk with computers. The study of reasoning using strict rules of validation of truth is called logic. So at the foundations of how we work with computers, it's not only mathematics as we saw earlier, but also logic. Statements that can be validated as true or false are known as propositions, although sometimes we'll just call them statements. A proposition, in other words, is a complete thought, often a complete sentence or a mathematical expression that has a definite and knowable truth value. Some examples include, Lansing is the capital of Michigan. This is a complete sentence and it has a definite and knowable truth value. In fact, we know that the statement is true. Chicago is the capital of Illinois. Also a complete thought with a definite truth value. It's false, and because we know it's false, it's a proposition. 5 plus 7 equals 12. Not an English sentence, but a complete mathematical thought that has a definite truth value of true. 7 minus 2 equals 10. Again, a complete thought with a definite truth value, this time false. Some non-examples, those are things that are not propositions, include Michigan is a beautiful state. Now, this is a complete sentence, but it's an opinion or a judgment call and cannot be objectively evaluated as true or false. I happen to think it's true, but you might not. Let's go to Chicago. A complete sentence, but this is an imperative, not a statement that is either true or false. You can agree that you'd like to go to Chicago, but this is different from saying that this statement is true. True, false values don't really make sense here. Where's the bread? Also a complete sentence, but it's a question, and questions don't have truth values. X plus 5 equals 12. Now this is trickier. This is a complete mathematical thought, but we can't tell if it's true or false because there's not enough information. This statement that the left side, x plus 5, is equal to the right side, 12, is true for some values of x, but false for others. Without knowing which x we are talking about, it's impossible to tell whether this is true or false. So it's not a proposition. Eventually, we will say that this statement is underdetermined, and we'll call such things predicates. Now you try it. Here are some statements, some of which are propositions and some of which are not. Pause the video and identify which ones are which. So these are the propositions here because they all have definite knowable truth values. The others are not, and I'll explain why. The first one is an opinion, not a statement that can be objectively true or false. This one is a question, and since questions don't claim that something is true or false, they have no truth value. This statement here, x mod 2 equals 0, is underdetermined. It's true for some values of the variable and false for others, so its truth value depends, which makes it not a proposition. However, this last statement is a proposition. It is definitely true that if x is even, x mod 2 is 0. What makes the difference here is that the variable x is quantified. We're putting a scope around the second part of the statement and claiming that x mod 2 is 0 for all even integers. Because we've quantified the variable and not just left it alone, we can evaluate the truth of this statement. We'll talk more about quantification in a later video. So in this video, you learned about what logic is and why it's important for computer science, what a proposition is, and how to tell the difference between propositions and non-propositions. In the next video, we'll look at some basic ways to build complex logical propositions out of simple ones using connectives.